Okay, so let's summarize what we learned last time. So we talked about the line integral of vector field. So let's say we have a vector field on Rn to Rn. Here we say that n is 2 or 3. So although we talked about two-dimensional vector field, we can also generalize to three-dimensional vector field. So when I talk about the vector field in this way, the domain set, the Rn, is usually the set of points. Okay? And I'm assigning a vector to each point in Rn. So the codomain space is the set of vectors. Okay? So you have to always be careful about what we are talking about when writing Rn. And we say that let C be a curve. So when I say a parametrized curve, then my codomain, the range is the set of points. Okay, so this is not a set of vectors. So this is also a set of points. Let be a parametrized curve. Then we say the line integral of vector field. So when I say line integral of vector field, it's different from line integral of real valued function. So I have a different notation that I take a dot product, which is inner product between vector field and this symbol d as arrow, meaning that it's a small infinitesimal vector that pointing to the parametrized curve. So, and this is defined to be, so this is just notation meaning that we are taking line integral of vector field along this parametrized curve, and this is done by first you plug in Ct to the f vector field. So what you get here is the vector, and you take the inner product with C prime t, which is also a vector. Now this is the velocity vector of parametrization, and you take the integration. So you have to be remember that this is the result of inner product between two vectors, therefore it's a scalar number. So we are simply taking one variable integration of one variable function to get a line integral of a vector field. Okay? So for example, let's say I have a vector field fxy equals to minus yx. So this is nice vector field, meaning that if I have 0, 0, then I have no vector, 0 vector. And if I add 1, 0, that means I move my vector field, makes the movement to the right-hand side. So you can think about this as a force field, or it's like a velocity vector of a wind at each point. So the direction of vector means the wind is blowing to that direction, and the length of vector means that wind is blowing that at that strength. So if I add the 0, 1, then I'm moving minus 1x. Right, so I think I made a mistake here. So it's if I add the 1, 0, then it's 0, 1, so I'm moving upward here. And if I add the 0, 1, then it's minus 1x, so basically this. And if you fill out all the other parts, you can see that this is actually going in spiral. And if you have a point away from 0 and more, then you see that the strength or the length of arrow, it gets larger. Okay. So if I want to integrate, if I want to find the line integral along this unit circle, Now, when you provide a parameterized curve for the line integral vector field, you should mention in which direction you're going to take the integration with. So I'm going to take a line integral counterclockwise. So that's my direction of the curve. And I'm going to parameterize that direction by what? Cosine t, sine t. And I will come back to the original starting point when t is starting at 0 and end at 2 pi, right? So let's try to find out the line integral of this curve. So just plug in numbers there. I have 0, 2 pi, and plug in there, I have minus sine t, cosine t. That's fct, and then inner product with c prime t, which is minus sine t and cosine t. So I have inner product between two vectors. That gives the scalar number, and I'm going to integrate that number. So basically, it's not just a constant number. It's a function in time in terms of t. So we have sine square plus cosine square. Basically, it's 1. So I'm integrating 1 from 0 to 2 pi. So I get 2 pi. So I make a remark before we move on that when we're talking about the line integral vector field, the parameterization doesn't change the line integral unless you change the direction of your parameterization. So the line integration of fct does not depend on the parameterization of the curve C unless the direction is reversed. So as long as you keep your direction same direction as the original parameterization, you can reparameterize your curve, which gives the same answer. For example, let's look at this example. So I'm going to find a line integral of this curve which winds the unit circle once. So I parameterize by cosine sine, and that's the standard parameterization. I can reparameterize, and let's say C1t, which is cosine 2t and sine 2t. So I wind this unit circle twice faster than original CT. Okay, so my t should range from 0 to pi in this case. If I use C1 parameterization instead of C, let's see what happens. So if I use C1 to find out the line integral, then I have a limit from 0 to pi and sine t, cosine t, inner product. And now we have minus 2 sine t, 2 cosine t, dt. So therefore, if I take the inner product, I have 2 sine squared plus 2 cosine squared. So I am integrating 2. So that gives the same 2 pi answer. Okay? So let's try to prove why we don't care, why the reparameterization doesn't matter to the line integral. So let's say I have C1, which is a reparameterization of original curve C, be another parameterization of C. such that I want to keep the same starting point and end point, and I don't want that the C1 has an interval that goes back and forth, and so that this messes this whole integration. So C1 T, C1 C. So C is the left ends of this interval of C1 is equals to CA. Will A is the left end of this original parameterization C, and C1D is equals to CB. And if I have to say in mathematical language what I just said, that there's no back and forth in the C1 parameterization, I should write in this way. So, and for each T inside of AB, there exists a unique S inside of CD such that CT equals to C1 S. Okay? So that means if I take the relation between T and S, so T range from A to B, and S range from C to D. If I take any point on T, I have a point in the Rn, or R2 or R3, that maps to a point in R2 and R3 by the parameterization of C. So CT is there. And I can always find a unique S that gives the same point as CT when I compute the C1S. So I can always find for each T a unique S that gives the same point on this Rn space. So that means, so by first two condition means that when T goes to A, I have a unique point in S range that which is C that gives the same point on the Rn. And also when T is B, I have a unique point which matches with when S is D. So I have a starting and end point. And in between, I can go from here to here in a straight direction, but it really doesn't matter because I assume that the C1 is an arbitrarily parameterization C. And if I have this point like this, then the relation between S and T looks like this. So as long as it's a one-to-one map, which means that it has no up and down, then I have a reparameterization of the same curve that doesn't go back and forth. Okay? So I'm going to call this function ST. Okay, so I'm going to call the value as S2. Okay. Now let's try to find out C1 FDS. So if I use C1 parameterization, I'm going to use the same, it's a formula, which is the limit integration from C to D of C composite C1. Here I have used this S as a parameter of C1, so I'm going to use S, okay? And then I'm going to take the inner product with S prime S. So if it's confusing to you, maybe you can use this different name for the S with the dependent variable S. But I'm going to use the same. I'm sorry. So this is. This is not S. Sorry, this is C1. Sorry. C1S. Yeah. Okay. And ds, right? And then let's replace every S in terms of T. So because S can be replaced by the function in terms of T, ST. So that gives CD, F, CS, ST. And then inner product, 1, 2, 3, okay. And inner product. And C1 prime S is ST, okay. And we have ds. So we can also change ds in terms of t, because we know that S prime t is, well, let's say ds dt equals S prime t, right? So I can use replace ds as S prime t times dt. So that changes too. So this becomes S prime t dt. And now if I change the integrating variable to t, then it's going to be the range of t, which is a to b. Because when S changes from C to D, T changes from A to B. Okay? So remember that, again, these parts are vectors. Okay? And this is these parts are, the scalar given by the inner product of two vectors. And this is also scalar. Okay? But let's say I can think about this scalar as a scalar vector to these vectors. So I'm going to combine these two components, which means that I'm going to take the inner product of this vector, the vector field, and this C1 prime vector multiplied with this scalar number. Okay? Now, let's rewrite this situation. So we have F and C1 composite ST, and then we have inner product. So again, so this is not the sign for the inner product. This is composition. And let's look at this one. So this is C1 prime ST times S prime T and dt. So here we have a vector field whose value is obtained when I plug in T. I compute the composite of two functions, C1 and S, and this value, which is the point, gives the vector and the vector field. And what do I get? What do I get after I composite these two functions, C1 composite S? So when I plug in T, when I have T, I first plug into S, right? So I get a value in this S range, and I plug in that S value to C1, right? So that gives this right-hand side here, right? I have T, and that corresponds to unique S, and I'm going to plug that S to C1. That's what I'm doing here, right? So that gives the right-hand side of C1, but we assumed that this is equals to CT, right? So basically what we are doing here is C1 composite ST is basically C1S, and that is equals to CT, right? Where, the same T is here. So this part is simply CT. This whole thing is CT inside. Now how about this part? So we have a multiple of C1 prime and S prime. So basically C1 prime is not a number, it's a vector. But why is a vector? Because C1 is a parameterized function. So it's C1 is 1 to 3 or 1 to n function. If you take a derivative of composite of two functions, two multivariable function, it becomes the multiple of two differentials of two functions. This is equals to C1 composite S prime T. Because, so you have a composition of C1S, and then you take the derivative. You first take the derivative of outside function, and you then multiply with the inside derivative of inside function. That's exactly this. Okay. So let's rewrite this last sentence. So that gives AB F CT dt, and then that part, and then inner product. Again, just be cautious. This is inner product. Okay, and then you multiply, and then what is C1 composite S again? So this is equals to C, right? So this is equals to C prime T. So I'm going to write to C prime T right away. So we get the original formula using C1 as a parameterization is equals to the formula when we take C as a parameterization of a curve. So basically, we are talking about the same line integral. Okay. So if you had reversed the direction of parameterization, then you are switching this the slope the opposite way. So we are taking when t equals a as this s equals to d, and t equals b as s equals to c. So we have a decreasing function s, and then we have used at first. Well, you can use the same argument, same formula, but the limit is changed. It's switched. A and b are switched. So if you want to switch back to a to b, then you have negative sign comes out. So therefore, there's one more remark that you can infer from that formula is that if C1 is a parameterization of C in the reversed direction, then if you take the line integral in C, that is equals to line integral along C1, which is the parameterization in the reverse direction, times the negative 1. Okay, so you just take the negative of the entire value. Okay. That makes sense because think about the force field and you're trying to think about how much work done has been done to the object that when you move one object from one point to another. So if you have a force field, like a gravitational force field, you can imagine, then let's say I'm moving my object from here to here. Of course, you know that it only depends on the height, but if you move your object to higher position, you have gained the energy. That means you have done the work, right? But if you are moving in opposite direction with the same along the same curve, then you lose your energy, which means that you have. So when you move your object upward, the object has gained the energy, which means that you have done the work. But if the object is moving downward, or if you make the object move downward, then you have gained the energy, right? So object has done the work to you, right? So basically, the work done to the object when object is moving downward is negative, right? It lost the energy. So that makes sense, right? In physical sense. All right. So that's what we have discussed briefly, and then also summarizes the line integral. Any questions before we move on to the surface integral? All right, so let's talk about the surface integral. So as we talked about the work as an meaning of the line integral, I want to give a situation that explains the surface integral. So let's think about there's a river, and there is a flow of a river, a flow of a water in the river, right? And you want to find out how much of water is flown through the river in a certain period of time, or let's say in a certain unit of time. You can take the unit of time as an hour or minutes or second, but I'm not going to specify that. But anyway, so we are trying to measure the amount of water that flown through the river in a unit of time. What we can do is try to put a sensor, or at least you have a measurement on one end of the river and to the other end of the river, right? And let's say you post some sensor, or you can put a human sensor there and then try to measure how much water has flown in that position by taking the bucket in the river and then try to say, okay, so put your bucket in the river for 1 second and then just pull out, and then see how much water has been flown into the bucket. So that means it measures how much water has been flown in that position, right? So what you have to do when you do that is, let's say, you put a line somewhere. So, and then you try to put your bucket in that direction, right? And then try to how much water has been flown into the bucket, right? But let's say water doesn't flow in this arbitrarily chosen direction, right? So water could be flown in this direction or in random direction, right? But you want to measure the water that flowed into that direction, right? Now, that direction is your direction of bucket, okay? But water is flown in this direction, okay? So you only want to measure the water. What you're actually measuring is the measurement of the water flown in this bucket direction, okay? So I'm going to take, so maybe I can exaggerate a little bit more. So this is the flow of water. So I'm going to explain this terminology again in the words. So I'm going to just picturize this situation and then explain it later. So how do you characterize this vector that is the component of f in direction of n? So first you have to take a cosine. You have to take the direction of n direction. So basically, you're taking this direction. And then the size of vector is the size of function f times cosine theta. So we have vector size cosine theta. But cosine theta is given by inner product of n and f. So cosine theta is f n. So maybe I put arrow here again. So, and then f n. Okay, so I'm going to plug in cosine theta there. So that means I have canceling of f norm, and I have one line here. So we have a square this n norm, and we have f inner product n. So basically it's f inner product n times n square n. So that is our vector, okay? All right, so let's try to find out the total amount of water flown along the river on a unit of time. Okay. So in order to measure that unit amount of time, that amount of water, well, first what we have done is try to set the line across this river. So I'm going to call this a CT. And at each point, I'm going to measure this thing across, let's say, this is small line segment of this CT. Okay. Then I'm going to assume that the water flown across this small line segment is approximately equal at the measurement at this point. Okay, that's fairly legitimate assumption, right? So this is going to be the sum of what? So these small segment has length C prime t. That's the value delta t. Okay. Okay. So we have been talking about this many times. So we have parameterized our line to measure the flow, and small line segment is achieved when you change your time scale in a small amount, which is delta t, along this C prime t direction. But we only think about this, the length. So we're talking about the speed times time, so which gives the distance. So it's just a small line segment, the length of small line segment. So what you have to do is small amount of water flown along this small line segment, and then sum those all up. So first, you take the length of small line segments of what would be the good name for this thing? The not reservoir. It's net. Maybe net. I will call it net. Okay. Okay. How about net? Okay. And then you multiply that with. So maybe you can put a unit for this amount, which is in terms of meters or centimeters or something. And you multiply that with how much water has been flown for each for a unit of time at each point, right? So you take this amount, right? So you're going to find out the length of this amount. So this thing is this contains the direction and the width, the direction and the length. Okay, direction means that you're measuring this direction, which is the direction of the bucket, and also the length of this vector means that in the unit of time, the water has flown into the bucket that amount. Okay, so the length is equals to Fn. So this is scalar again. So more maybe just this scalar here. I'm not going to take the absolute value here because water could be flown outward from the bucket, right? Water could be flown in opposite direction. That means you have a negative sign here. I don't want to make a negative. I don't want to erase the negativity of that situation. So just the scalar here. And then you take the absolute value here, what you get is divided by the length of n, because you have, if you take the norm of n, it will cancel out with the square of norm of n in the denominator. So this is the length. I'm going to compute this one. So that means the amount of water flown at unit distance on a unit time. So this is going to be the length, c prime t, delta t, and this is going to be Fn times n. Okay? All right, let me assume one more thing. So when we think about the direction of your bucket that's trying to measure how much water has been flown, you don't have to make your vector n to be a vector with length not equals to 1. So you can always assume that your bucket, you only care about the direction of your bucket, not the size of this vector. So I will assume that this n is always a unit vector, right? So there's no meaning, there's no point having non-unit vector in a direction of your bucket. So I can simplify this more. So this will disappear as 1. So what happens is, in order to try to find out the total amount of work, a total amount of water that flown in along this river, is that you take Fn c prime t dt, and let's say we have parameterized c as AB2 R2 in this case. Then this is integration of A to B of F composite n. I'm sorry, so it's not composite. I've been confused again. So this is the inner product. Okay, so F inner product n multiply with c prime t dt, right? So let's reinterpret what I have done. So this measures total amount of water flown through the water, but that means water doesn't expand or shrink in a volume. Okay, so water is incompressible material. So it should be the same amount whether I put my net in this way or this way. All right. So yes. Yeah. 네. Oh yes, yes. Divide by. Right. Okay, well, let's talk about the configuration of net, the independence of this amount on to the configuration of net later. But let's talk about what this is called in usual sense. So whenever you try to find out how much of your, well, how do I say it? So I projected my vector field as a thing that gives information about the direction and the speed of water flow. Okay, and I'm trying to find out how much water has been flown through some section of this river, and then that's how I write it in a long description. But that's simply called the flux. Okay. So if you think about not a water flow, but like a vector field or some wind blow, then this flux also means the similar thing. If you put your object on a vector field and try to move your, not just single object, lots of particles, like small particles, on a space with a vector field, then the particle is moving because of the vector field, right? If you have a magnetic field and then you have some electrics, then you electron, then electron is moving, right? Not a magnetic field. Oh yeah, magnetic field, right? So if you measuring how much particle, the amount of particle that moved because of this vector field or magnetic field across this some section is called the flux. Okay, you think about this, the particle of water that flow into the sections here. It's same as when you think about the electron particle or some very light-weighted particle that's flowing along this air because of the wind vector field. Anyway, that's called the flux, and we are trying to find the flux across this one-dimensional section. Okay, so that's how we get the flux. So let's think about this terminology here. So what is N here? So we had a net, and this section is parameterized by CT. N is also parameterized by T. So T specify what point you're looking at, and N is the normal direction of the net at that point. Okay, so this is my NT. Let me give an example. Let's use the same example. So we have fxy as minus yx, the vector field. Okay, and then I'm going to take my ct as cosine t, sine t, but not from 0 to pi, 0 to 2 pi. I'm going to take t from 0 to pi. So that basically I'm take a right hemisphere of the circle. And I'm trying to find out the flux of this vector field. So that means how much particle is moving to this direction. Okay. So at first, so there's one very important concept that should mention before we talk about that. So when you draw the picture, when I draw this picture, I kind of assume that I want to measure the direction measure the amount of water or flux in this direction. Okay, that direction is arbitrary. I could have used this flux this direction, the opposite direction. Okay, so whenever you try to find the flux, you have to mention in what direction you're trying to get the flux. So in this picture, I'm trying to get a flux to the right-hand direction, right side direction, okay? The eastward direction. So my N, or T, is the normal vector to the curve CT. So whenever we try to mention the direction that we want to find, that we want to care about, is the following. So such that NT inner product I is always bigger than 0. So remember that I is 0, 1, 0, 0. In this case, I'm taking I as, because we are talking about the two-dimensional space, so we just take I as 1, 0 here. So that means if I take an inner product with this normal vector with 1, 0, I always get a positive inner product. That means the angle is bigger, less than pi over 2, right? So we know that this n is the eastward direction. So whenever you try to find the flux, this normal direction has to be mentioned clearly. Okay. So let's find the flux. So basically, we call it flux of F across this curve C. Is just use the same formula here. We parameterize t from 0 to pi, and what we are doing here is we take an inner product between f and n. Well, basically, when I take the inner product with f and n, I'm taking a vector field at the point ct, right? So not just fxy. I'm plugging the xy when t equals to when point is equals to ct. So I'm taking a vector field at the point ct, okay, and then I take an inner product with n. You should find n. So let me, before I find n, I just write it nt for now, and then c prime t dt. So let's try to write my nt. So I want to find the formula of n in terms of t. So when I am at cosine t sine t, so that means when my vector is pointing to that direction, okay, I want to find the normal vector, which means that it's orthogonal to the tangent line, which is also a length 1 as n. So what should be my n? So n is a normal vector to the tangent line at the point cosine t, sine t. But I already gave you the answer here. So when I take cosine t, sine t as a vector from the origin to the point here, it's already automatically normal to the tangent line at the point cosine t, sine t. So and also this cosine t, sine t as a vector is also norm 1. So I can use nt as this one. So it's a cosine t and sine t. And let's now plug in values. So ct is cosine t sine t, so I'm going to plug in there. So this is minus sine t and cosine t. And then inner product with cosine t sine t. And what's c prime t? I get minus sine, cosine, but I take the norm of that vector, which gives square plus is 1. So it's always 1 here, so I get d1. Okay. So what's this? What's the inner product? 0. So we are integrating 0. So therefore, it's 0. So what does that mean? Nothing flowing across, the net flow across this border, or across this section is 0. But what happens in this case is it's not that at some point we have a positive flow and the other point we have negative flow and net flow is 0, but we have 0 flow along every point on this net, because vector is flowing at the tangent direction of this border, right? So if you think about the direction of vector field at this point, it's a negative y, comma x. So it's following this direction. So whenever you try to find the flux, you have to find out how much particle is moving in the the normal direction to the net. But this particle is moving in the tangent direction of the net. So we have nothing flowing across this border, across this net. So basically, it's zero flux along at every point of this net. So therefore, it's zero. Zero flow, every point. So it's zero. But it's possible that it's other situation, not like this one. You could have a positive flow and the negative flow, and the net flow becomes zero. Okay. And then let's try to generalize the situation to the three-dimensional thing. So we have two-dimensional vector field. Let's talk about three-dimensional. So let's say we have a two-dimensional net. Okay. Let's say this is a surface S. And then we are trying to find out how much particle has been flown through this net by the vector field. Okay. The flux of the vector field F, let's say R3 to R3 across the surface S. I'm trying to find this, okay? So what I have to do first is to find out the small portion of S. Let's try to subdivide these S. And think about very small part of S here, let's say delta S, okay? And if I enlarge this picture, this delta S almost look like this parallelogram in three-dimensional. And there is a normal direction to this parallelogram. So this is delta S. And there is a vector field flowing in this direction, F. Okay, so, and then let's say this point is parameterized by two variables, two coordinates, u and v. Okay. So let's assume that S from let's see, A, B, C, D to R3, where it sends UV to X, Y, Z, is a parameterization of S. Okay, so what I'm trying to get is my delta S. Delta is here is a set. Okay, I mean, I'm talking about delta S as a set, which is the small portion of S. It's an image of this parameterization S again of small part of this rectangular domain of S. So we talked about this when we talked about the surface integral of a real-valued function. Let me write it here. So I'm dropping all the index I and j for simplicity here, but if you want to, you can put the index ij here, ui, vj here, and just ui, vj everywhere, okay? So, this S is a map from two-dimensional UV plane from A, B, C, D to three-dimensional space, R3, in X, Y, Z coordinates. And if we take the small portion of this, let's say this is UI and this is Vj, this rectangular portion is identical to, one-to-one map to this portion, which is delta Sij. So I'm talking about that situation. So if I enlarge this part, this is our delta S, and this point is SUI Vj, and we have a normal direction and F. So normal direction and F also measured at UI Vj. Okay, it changes. It changes at every point. Let's try to find the flux. So that's the sum of small fluxes, right, for each ij. So how do you get the small flux? You try to find the flux across this delta Sij, right? First of all, this measures the point flux. So at that point, how much particle is moving across this point, right? But then you have, if you multiply that with the area of this small size of surface, then you get a total flux. So first, we take the area of delta Sij, and then multiply that with the flux across this plane. But now you don't measure this total, this amount. You only measure the amount that flow in a normal direction, right? So how do you get the portion of normal direction of this original vector field? Same way we did in the two-dimensional case. First, you take F, and then you merge inner product with N, and then you take as a scalar and divide it by N. But also here, we assume we always have the normal direction as a unit vector, okay? So that we don't care about the size of N. So that's that, okay? So how do you take the area of delta Sij? We've actually done this before in a surface integral of a real-valued function. Delta Sij looks like this, almost looks like parallelogram bounded by two vectors. And that two vector is given by the vectors corresponding to the u directional vector and v directional vector. Okay, so the area, you can look up the previous lecture if you want to, if you forget about how we did it. It equals to, actually this approximately equal to SU cross SV. And take the inner product. I take the norm of that cross product. Of course, we are talking about this vector at UI Vj, so you have to plug in this value to find out actual number here. And that's everything, right? So we have total flux is equals to sum of area. I'm going to drop UI Vj for now as U cross SV. Sorry, so put this delta U delta V. And delta U delta V. And then what? Multiply that with F inner product with N. Now, let's find out what N is. How do we find N? So we found the area by taking cross product and take the norm of that cross product. What does the direction of cross product gives you? It gives the normal direction of your curved surface. So you see that this is your curve, a portion of curve of Sij. And let's see, this one was SU, this one was SV. If you take the cross product, you get a vector which is perpendicular to SU and SV at the same time. So this is the normal direction. Because although I exaggerated very much of this very small portion of it of the surface, it will always look like a just planar parallelogram. So if you think about the parallelogram, then you have SU direction and you have SV direction. The normal direction to SV and SU is going to be the normal direction of this parallelogram, right? So this is SU, SV. Now, the cross product satisfies the right-hand rule. So if you're trying to find this direction, because I used SU, it's in front of SV. So SU, SV is direction of your forefingers, and then the thumb is directing the direction of the cross product. If you want the other direction, then you have to use the inverse cross product, so SV cross SU in this case. So here, really we need to define our normal direction here, but assuming that we have the direction that we want to find the flux of crossover, then you have to find out in which order that you have to take the cross product between SU and SV. I'm going to talk about with a concrete example afterwards. So anyway, let's assume that we have this direction as our normal direction. And then what we have to do is find out the unit vector which has the same direction to that normal direction, right? So we're going to inner product with SU cross SV divided by SU SV. Okay, so that gives the unit vector, and yeah, that's it. So that's the net flux, approximate net flux, and that gives what? The surface integral, because you simply a double integral at least. You can change your delta U delta V to du dv, and then everything is just scalar number in terms of uv. So we have f in terms of uv, because if you substitute your parameterization here, so and then you inner product with SU cross SV, and then what happens to these two vectors? It cancels out, right? So we don't have anymore. We don't have this anymore, and du dv, right? That's a total net flux across this surface. How do we call this in a simple way? First of all, this integration is about u and v, and our range of uv from a, b to cd. But this is equals to, this looks like the surface integral, right? Because if you take this thing as a scalar number, this is simply looks like a double integral, and you can interpret your double integral in terms of surface integral. Or another way, if you think about, again, how you change your variable integration by substitution, use this integration by substitution. Let's think about this situation. So you have SU, SV, SU, SV, the unit normal vector on the surface here, and then you inner product with F, and then you take the S here. when we define the surface integral in this way, we needed this factor, right? If you use the formula of your surface integral using the parameterization of a surface in terms of u and v, this factor appears. So basically, you're going back to this original situation, right? This is equals to AB, CD, F, S times SU, SV, SU, SV, multiply SU, SV, du, dv. That's the formula. That's the definition. The first two factors, and this is inner product. So this factor is just integrand. This is the Jacobian. It's not a Jacobian. It's a kind of Jacobian. It's a factor that modifies the areas, right? So that was the definition of the surface integral, right? So if I replace this with a symbol n for simplicity, meaning that I'm going to take a normal vector of unit normal vector at every point on the surface, and then take the inner product with the vector field f, then this can be written simply as f inner product n times ds, okay? And then if you simplify more, you don't really need to specify n, because I can simply take this n times ds, the small increment of s, well, the small increment, it's a small value, small area of s, as a vector, simple vector. So this is also written as f ds. So this is a vector which is in direction of normal vector and whose value is the small area of the surface at point. Okay, so yeah, well, let me not use this, just a notation. So there's no meaning to it, just notation. Okay, so this is called surface integral of a vector field, and this is called a flux. Okay. Let's look at example. Very simple example on three-dimensional case. I'm trying to take a constant vector field. It's always upward direction. Okay. So at any point x, y, z, my vector field is moving upward, and I'm going to parameterize. I'm going to use the surface S as an upper hemisphere. Okay, right. Upper hemisphere. I'm trying to measure the flux. Now, whenever you try to find the flux, you need to provide in which direction you're trying to find the flux. My direction is, which means that I have to specify the normal vector to each point of the surface. So my normal vector is this. Okay, so upward, kind of upward. So the normal vector n on S is one that satisfies this inequality, which means that in any direction of n, if I take the inner product with 0, 0, 1, which is k vector, then it always have a positive inner product, which means it has an angle less than pi over 2. That means I know that it's always upward. Okay. Now, we have a normal direction. Let's find out the flux. the flux across this surface in upward direction is well, let's go back to the most specific form of this flux. So this is the most specific form. First of all, in order to use this formula, we need to find out the parameterization of surface, written as S. So SUV parameterizes this upper hemisphere. Let's use the spherical coordinate because we are at the radius 1, and we only change theta and phi to parameterize the surface. Let's say U is used for phi and V is used for theta. That gives, first of all, theta phi. Okay, so theta phi, for example. I'm going to take a sine U, cosine V, and sine U, sine V, and cosine U. That's going to be my parameterization of the hemisphere, but I have to specify the range. So U only ranges from 0 to pi. That is theta, okay? So we have, not pi. In this case, pi over 2. If it goes to pi, then it goes to the lower hemisphere. And V serves as a phi, so it runs from 0 to 2 pi. So I'm going to integrate that. Or maybe I put this sign first. 0 to 2 pi cross 0 to 2 pi here. And the vector field is computed at SU, V, which is these x, y, z coordinates. And then I take an inner product with normal vector n. Now I have to find out what normal vector is. Let's say this is our normal vector at this point. So I have to find out normal vector n with a cross product of SU and SV. The thing is, in which order I have to take the cross product to find out the upward direction. So let's try to draw SU first. So at this point, SU, S partial derivative U, is the vector I get when I change U but fix V. If I change U, I change the is it called the longitude? Latitude, right? I change the latitude, right? So I'm moving downward direction. So this is my SU, okay, at this point, right? So if I keep changing, if I keep increasing my U, my point is moving downward. So infinitesimal direction of movement is this direction. And what happens when I change V but fix U? I have changing the longitude. So my velocity vector is this direction. So U serves as phi, as theta, and U serves as theta, and V serves as phi. So if I have fixed this direction, in order to find the upward direction of the normal vector, I should take the cross product between SU times SV order, right? So that means I get the right-hand rule to get sum is directing upward, okay? So SU, SV divided by SU, SV, and then I have I have this term, so I already canceled it, so I don't have to normalize. So du, dv, okay? Let's find out the computation. So actually, this part is not a function of uv because I fixed the function, fixed the vector field as constant vector field. It's always 0, 0, 1. Okay. 0, pi over 2, 0, 2 pi, 0, 0, 1. That's the vector field. And then inner product with what's SU? Let's compute it here and then plug in later. So SU is cosine U, cosine V, cosine U, sine V, minus sine U, right? And SV is sine U minus sine V, and sine U cosine V, and then 0. So if you take a cross product between these two vectors, you can imagine that there is a 3 by 3 matrix in these places. So think about what you get when you take the cross product. SU cross SV. What comes to the coefficient of I? So this disappears and this survives. So we have S square UCV, right? And then what comes to the J component? You have canceling with this, and you have surviving this factor. That's a plus factor, so it's S square U S V. So S means sine and C means cosine. And what comes to the coefficients of K? So we have CU SU CV CV plus CU SU SV SV. So C square V S square V added to 1. So basically we have SU CU. Okay, so that's the cross product. I'm going to plug that in here. S square U CV, S square U SV, and then SU. Yes. Which one? The last one? K C S S. Right, but you have plus here, you have minus here, but why there's no minus here? Here, SU, U, U, U. Okay, so SU, CU. And du dv. Okay, what do you get? Right, you only get this 2. So let's try to use the Fubini theorem. So first you take U range from pi over 2. And then V from 0 to 2 pi of sine U, cosine U, dV du. So when you take the integration of V, it doesn't have any V here, so it's a constant, so it's 2 pi. And when you take the integration of U, maybe it's 1 over 2 sine 2U. Right, so integration of 0 to pi over 2 of sine 2u, right? 1 over 2 sine 2u. So we have du, and we have 2 pi times minus 1 over 4 cosine 2u of 0 to pi over 2. So we have pi over 2 times 1 minus 1. Oh, is it right? So 1 minus 1. 1 minus minus 1 plus 1. So we have pi, right? It makes sense. Why does it make sense? Let's think about our situation again. So we have a constant flow to the upward direction. So you want to measure how much is flowing across this hemisphere. But you could have, let's say, suppose that it's a water flow, okay? You could have measured this flux using this planar surface, right? Instead of using this hemisphere, you could use this disk to find out the measurement, find out the flux across this surface, right? It should be the same. If you think about it as a water flux, then what do you get when you use this surface as a surface to find out the flux across? So let's say this is S prime. Let's try to find S prime flux. We know that this F is 0, 0, 1, okay? And what is the normal direction to this S prime? It's always constant 0, 0, 1, right? Now you don't have to even parameterize your surface S prime, because always the normal direction is 0, 0, 1. So this ds is n times ds. So this ds doesn't have a vector sign here, so it's just the ds here. And n is 0, 0, 1. So you're simply multiplying an inner product these two vectors, which is 1, right? So what you get? To get the flux across this disk, you can get this flux simply by integrating the surface S prime 1, integrating 1 over the surface S prime. What do you get after you're integrating 1 over the surface S prime? It's the area of S prime. It's pi, right? The same answer we got. So it should make sense. Any questions? So let's summarize what we have discussed so far, because the next topic is very important. And you have to understand the meaning of the line and surface integral to really understand what's going on in the next topic. So line integral measures the work done by the vector field on the object along this curve in that direction. And also the surface integral measures the flux across some surface S along the normal direction of a surface. Now, we always talking about the surface with a certain normal direction, but there is a surface that doesn't have the normal direction, which means that there's a surface that we cannot orient the normal direction in a consistent way. So let's see. Let me talk about the remark. The orientation of a surface S is a continuous vector field N, which is defined on the surface S to a three-dimensional vector field, a three-dimensional vectors, such that the size is always 1. So we always normalize this as normalize this normal direction. For example, there is always actually there are always two orientation of on a surface. And there's a big assumption there. If the orientation exists. So if the orientation exists, there's always two. So for example, if you have a surface as a sphere, then you can take one orientation as an outward orientation and the other orientation as an inward orientation. Okay, like that. So if this is a closed surface, but if you have an open surface which has a boundary, you can always also choose your orientation as an upward direction and opposite direction, which is inward direction, downward direction, like this. But there are surfaces that does not have any orientation, which means that you cannot find out which one is upward and which one is downward. You cannot differentiate these two. So for example, the most famous one is the Möbius band. How did I draw this? Okay, just okay. So this is Möbius band. Okay, so you twist once, twist not 360, just twist 180, and then glue this together. You get the Möbius strip. So why this is not? So this kind of surface is called a non-orientable surface, and why this is non-orientable? Think about you choose one orientation. Okay. So this orientation has to be continuous, which means that if you move your orientation along any curve on a surface, you should find the same orientation when you coming back to the original point. So think about a point in a Möbius band and then try to put a one direction of normal direction. And then let's say you try to move your normal direction n along this center line. So along this center line and coming back once. So this line, now it's twisted at here. So it's going to be this direction, okay? When you twist it here. And also it's still in the same direction, which is inward direction. And when you're coming back to the original point, it's going to be inward, right? So you have exactly opposite direction when you loop around one cycle of the surface. And it doesn't make sense because in order to have a flux, you have a consistent direction of your normal direction. So you cannot find a flux. It doesn't mean defining, it doesn't have a point when you define a flux across this non-orientable surface. So when you're talking about the flux across the surface, you always talk about the orientable surface, which means that you can give an orientation to the surface. So the flux of a vector field is defined only for the surface which has on orientation. Okay. So similar to this line integral, if you change the direction of your line, parameterization of a line, you have a negative line integral, right? What happens when you change the orientation of your surface, which means that you change the normal direction to the opposite direction of the original normal direction? The flux after you get is the negative of the original flux you get with the original normal direction. So when the orientation is opposite, then the surface integral is negative to the original surface integral. Okay? Now, so we are done for today. I'm going to just give a preview of what we're going to discuss next time, right? For a few minutes. Any questions so far? If there are any questions, I can answer now. Okay. So what we're going to discuss is that, first of all, let's think about a closed curve, which means that the starting and end points are the same. And we have a vector field defined on a surface, defined on a plane. And this plane contains this entire curve. Okay. Okay, what happens when I take the flux across this line, closed curve of this vector field? So you see, there is a portion of a line that flux is coming inward, and there is a portion of a flux that comes outward. Okay. So what should be the net flux of this entire curve? Maybe zero, right? If it's a water flow, which means water is incompressible material, then whatever goes in should goes out, right? The amount that goes in should go out exactly. But what if, let's say, you have a heating plate, and then somehow you're trying to find out the flux of air, right? So what happens to the air when you heat the what happens to the air when you heat the air? What happens to the volume? Increases, right? So whatever goes in has a low temperature, but inside it has gained the temperature, so volume is increased. So what goes out could be more than goes in, right? So if you have a closed curve and try to find the flux across this closed curve, the net flux may not be zero. So how do you actually compute? I mean, you can compute the net flux if you have entire vector field, but suppose that you don't know what's going inside here. How would you find out the net flux across this closed curve? That's the That's actually the two-dimensional version of the divergence theorem. And also, we're going to talk about the Stokes theorem, and Stokes theorems talk about the relationship between the line integral and the surface integral, and it involves the curl of a vector field. You probably have seen this symbol in the physics. So, in my point of view, if you try to interpret the meaning of a curl of a vector field, you need the Stokes theorem. And then not the meaning of curl gives the meaning to the Stokes theorem. Stokes theorem gives the meaning to the curl. So if I just spoil the result, this curl gives you how fast does your vector field rotate your object when the object is affected by the rotation of the object is affected by the vector field in the space. So we're going to discuss two things. One is the Stokes theorem, and the second is the two-dimensional version of the divergence theorem. And with that, we're going to discuss about the meaning of curl of a vector field and divergence of the vector field. And once we've done that, we're going to generalize our Stokes theorem and the divergence theorem to the higher dimension, and we'll see that these. I forgot to mention the Green theorem, but there is a Green theorem which is the two-dimensional version of Stokes theorem. Anyway, the Green theorem, Stokes theorem, and divergence theorems are actually the same thing. They're not different. They're actually the same theorem, which is just in the calculus textbook, they try to make it simple as possible that they put different names to it. Of course, they're actually the contributors' names, but they are actually the same thing. They're all Stokes theorem, basically. So that's our plan, and I'm going to give you one more assignment to the homework. So which is the question section that you have to describe what line integral and surface integral is. So once you have answered that, you're done with it. And if you have more questions, then you can pose more questions to your own pages to get more extra credit. I mentioned again that I'm going to close all your pages on 3rd of December. Yes, 3rd of December, which is the Friday. And then try to score your results. So finish your assignment before then. So one advice is that I think your concern is mainly on the project topics, but don't make project very hard topics, okay? So make it very simple. It could be really, really simple. Just your point clear. Just make your point clear and then writing clear, okay? Don't make a big goal and then make a small result. Small goal and concrete result is way better. All right, so thank you for listening and see you on Friday.